I want to double check papers. Mitchell Fairgrieve, are you here? Austin Shaw, David O'Donnell, Chris Squatch. Chris, where are you at? David. Chris Squatch, you're not here? Delane Russell. Delane Russell, are you back there? All right. Okay, I'm still working on your exams, and I'm almost done with these homeworks. We just have a few more to go. Where's Chris Squatch's table? He's over here somewhere, right? Can you tell him he's got a paper when he gets in case I'm occupied with something? Yeah. Yeah, I have to give it to him. I can't hand out back papers except to the student. Thanks, though. Appreciate it. All right. Our outline for today is to do well, it's a simple problem, but it's gonna burn your brains out on iClicker. So it's a deluxe question. And then what we'll do is, and it's about centripetal motion, centripetal acceleration. Then what we'll do is we're going to analyze some of the classwork data from session 11. And what I'm going to do, while you guys are working on the iClicker question, it's going to take a few minutes. So while you're doing that, I'll fix up a discussion area where you can download the file, all right? And then for your group, and everybody in each group, you've all got a computer. Go ahead and log into that and get into Webcourses. At least one person only, and that'll be for the entire group, okay? And then we'll do some problems after that. And homework 4, does anybody want to know about homework 4? Homework 4, we're a little bit off schedule with the homework, but we'll deal with that. I have a plan for that, involving my trusty assistant, Tyler Campbell, the first. Long may he reign. We're going to do homework 4, and it's going to be like the Spider-Man problem. I'll just tell you straight out. It's going to be something like that. So the problems that we do in part 3 today are going to be, that's going to be one of them. We're going to do a couple 3 problems, hopefully. So here's the SARC schedule. Anybody go yesterday? One person? Boy. All right. So let's do some numerical answers. I got to turn off. All right, so turn on your clicker, hit the refresh key. Here it is. Given a 45-degree launch of a projectile with initial velocity vector 100 meters per second at a 45-degree angle, calculate the angle of the centripetal component of the acceleration. Right, so this is a ballistic arc, parabola, and calculate the angle of the centripetal component of the acceleration at time t equals, excuse me, at time t equals 4.0 seconds. So I made most of the numbers, nice round numbers, 45-degree launch, that's century, because I want to, because the centripetal component angle is the tricky part. Unless you see it. All right, so type in the numeric part of your answer to the nearest 0.1 degree relative to the rightward x-axis. All right, so that means first quadrant direction, that would be a positive angle because it's above the x-axis. All right, if you get it, and I don't know what the answer is yet either. I just thought this up before class. So if you get something down the fourth quadrant, it's either going to be first quadrant or fourth quadrant. Somewhere to the tilted upward to the right or downward to the right, because that's the direction of the motion. That's the first half of the what do you call it? The trajectory. All right. So because it's not up to apogee. Apogee is going to be about 10 seconds. So 4.00 seconds is going to be a little bit below that. So you're partway up the parabola. All right, so if you get fourth quadrant angle and just graph it out, do a nice sketch, and then that if it's fourth quadrant, then you'll be negative. And what you're doing, it shouldn't be any. If you do this right, it shouldn't be any problem to figure out the exact angle if you work it out properly. All right, so go ahead and start on that, and I'm gonna. I'm going to try to click out of here. I can't click out of here. All right, so go ahead and write this stuff down because I'm going to pause the podcast. No, wait a minute. I think you can keep going. I've only got 59 answers. How many students have we? Can you guys make a count? We have a lot of absenteeism here today. Hurry up. I want to close the problem. '84. I want one answer from everyone, not by teams. You're working in teams, but everybody should click in their answer. I'm going to give you 1 minute to click, and then we're going to stop the problem. So hustle. Okay. 30 seconds. 20 seconds. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, if you're not answering, God bless you. You had almost half an hour. All right. Let's take a look at the solution for the brain burner. All right. Can you switch me over to the document camera, please? And I don't know what the answer is, so let's just try to work it out. And we'll double check the answers that you get with what I get. And I'll embed this into the YouTube as always. And then when we're done with that, we'll go through the money toss problem. Okay, so this is February 13th, 2020. Brain burner. Okay. I'm going to draw a rectangle here to represent my initial velocity vector, our standard 45-degree. So I wasn't trying to make the customary tasks that we've been doing in the past. anyways, this is, let's see, this is 70.7, is that correct? Meters per second. Anybody verify me on that? Yeah, that's 100 times the square root of 2. And so this one is, so I didn't care to make this difficult here, but the same philosophy applies. So that's your initial, and this means that you have Vy of 0, and this means that you have Vx of 0, and that's actually Vx for all times. But this one's changing. The initial component is changing. So Vy of t is whatever you start with, Vy of 0 plus gt. All right, so that works out to 70.7 meters per second plus a negative 9.8 meters per second squared times t. And so now, why are those two equations here and here, these two equations, why are those important? Because the definition of centripetal is always perpendicular to the velocity, perpendicular to the path, and that's defined by the tangent vector, the velocity. All right. So if we can figure out the angle of the tangent vector velocity, then we can figure out 90 degrees from that. Now I'm going to draw a nice big. Is there a protractor around here? Do you see one nearby? It's all right. I'll just draw by hand. A ruler? Yeah, let me use that ruler. All right, I'm going to draw a nice big half of a baseball problem here. Nice and big. And you'll see how to tackle this. Okay, so that's 6. And this is 6. This is just, 45 degree makes the, there's 1. And then 1, 2, 3, 4, 5, 6. All right, so here's the next box. And then here's the top of the box up here. So this is, instead of the 4 rectangle method, it's the 2 rectangle method for drawing half of a parabola. And this is a 45 degree launch parabola. Is that right? 1, 2, 3, 4, 5, 6. Okay. All right, so here's your launch point down here. So this is 0, 0. And here's apogee up here, which we could get the coordinates of that, but we're not even we don't need that. But what we do need is a nice picture of a parabola that launches at 45. So here's the diagonal of the first box. And no matter what the launch angle is, the diagonal of the first box is how your parabola launches. So it starts out along this path, and then it gradually diverges and comes horizontal up here. Hey, that's the best parabola I've done so far this semester. All right, so there's your path. Now, let me darken that in with ink. Actually, let me use my blue ink. All right, so it stands out on the Instagram. I notice a lot of you guys are inviting me to look at your Instagram, but to join your Instagram or whatever. But I've not accepted a single one. But you guys can see everybody that I've been following. All right, so there's your parabola. Now I'm not going to make I'm not going to make an accurate position. I could make a pretty accurate position if I wanted to know x of t and y of t, x of 4 seconds, comma y of 4.0 seconds, I could do that. But all I need now is to use the strategy of the vector. Now, I'm going to assume that 4 seconds, this is going to be about 10 seconds to here. So let's see. So 5 seconds would be right here, halfway. This is the 5-second mark. If this is 10 seconds here, and this is 5 seconds here, so 4 seconds. Let me make it right here. Now we're just going to estimate it there. So that's my position at. Now, notice that I've diverted. I'm not sure that's where it is. It'll be somewhere close to that. I'm a little bit off the 45-degree line, as you can see. All right, and now I'm going to draw in the velocity vector at that point. All right, in red. Now I'm going to make it nice and big here. All right, so that we can see it. Okay, so there's my velocity at 4.00 seconds. All right. Now, perpendicular to that, perpendicular to the path, is the tangential or the centripetal acceleration vector. Centripetal anything is going to be perpendicular to this. So centripetal acceleration, A of t, A subscript centripetal at 4.00 seconds is perpendicular to V of 4.00 seconds. Okay, so there's the secret. There's the concept that you have to use. And that's true no matter what the shape of the path. Now this one's fairly easy to figure out, but if you have a really complicated path, you would just do it numerically, you know. And the key numerically is figure out the slope, you know, y equals mx plus b at the point that you care about, and then go the perpendicular line is -1 over m, and that'll always give you the slope of the perpendicular line. Then you can work from there. Anyways, so let's figure out v at 4.00 seconds. So it's going to be a little bit less than 45. So let me just write it about like this. All right, v of 4.00 seconds, and then here's my reference. Here's my positive x-axis for reference. Okay, and so we know that, so we can figure out the components here. So let's do that. Vx of 4.00 seconds. We know what that is. It's 70.7 because it doesn't change. So that's the cinchy part. Did anybody do that? Everybody got that? Okay, so that's the cinchy one. So that's this one, 70.7 meters per second. So now this one's going to be a little bit less than that. And I know that the y is going to be a little bit less than that because I know that it's going to be, if it was equal to 70.77, the tilt angle would be 45 degree here. But that only happens at the launch. So this thing's going to be a little, so it's going to be 70, this will be 60 point something, who knows. All right, so we're going to figure that out right now. Vy of t, Vy of 4.00 seconds is equal to, okay, starts with 70.7 meters per second. And then we take away -9.8 meters per second squared times 4.00 seconds. Okay, so that's, what is that, 39.2? Is that what that is? 9.8 times, let me clear this, 9.8 negative times 4, 39.2. Okay, so 70.7 minus 39.2, oops, 70.7 minus 39.2, 31 point, what? That doesn't seem right. 31.5, is that what you guys got? Wow, that's quite a bit less. So so what that tells me is that I underestimated the 4.0 position. It's probably a little bit closer up here. But we're going to let the numbers do the talking. So Vy of 4.00 seconds is 31.5 meters per second. Okay, now the tangent of this angle here, all right, is going to be 31.5 divided by 70.7. So 31.5 divided by 70.7. So that's equal to theta. So that's equal to, let me do this on the calculator. See if you guys verify me. 31.5. Wait a minute. This is different from the. Okay, so inverse tangent 31.5 divided by 70.7 equals 24.0. Anybody verify me on that?
Yes.
Okay, so now that's the angle of the velocity vector. Subtract 90 and you'll get this angle. So that'll take you down into a negative, negative angle. So what I'm going to do now is I'm going to draw in. Let me write this in with red here. So here's red for my velocity vector, v of 4.0 seconds. Okay, so that's in red now. And now let me kind of eyeball this in. Actually, I could do it pretty carefully here. Let's see, this is 1, 2, 3, 5, and up 1, 2, 3.3. So I'm going to go down 5. 1, 2, 4, 5, and over 1, 2, 3.3. That's not right. Oh, got from here. 5. Here it is, right here. All right, so I'll do this one in blue. So this is your, and we don't have the magnitude of it, but we can get that in just a second. All right. So there's your centripetal acceleration vector right there. And at this instant of time. So let's see, 90 minus, or 24 minus 90 is what, 66? All right. So, and it's negative. So, so the direction is negative 66.0 degrees. Okay. And now if you want to figure out the size of the acceleration, now you have to do a little bit of trig. And here's the vertical. Let me do this in pencil. So here's the y-axis. All right. And so that's going to be the direction of g. The tangential part of the acceleration is going to be perpendicular to the centripetal, and so it's going to be back this way. So here's the tip. We'll make it this big. Okay, and there's the tangential. All right. So this angle here, I'll call it alpha, is 20. That's 24. So right. So, or no, that's theta. That's theta. And this angle is alpha. So alpha equals minus 66 degrees. We'll call that, just so we have uniform notation. This is 9.8 meters per second here. So that's the key there. Once you get this velocity, or the velocity figured out in the angles and stuff, then you can build the, from the 9.8 vertical, now you can get components in this direction and this direction as well. So, so let's look at this. A subscript C magnitude is equal to G times the sine of theta. Anybody figure this out? All right, so let's figure out what this is going to be. So this is going to be the magnitude. So it's going to be a negative. Well, we'll just give it a positive magnitude. All right. We can worry about the signs later. So G sine theta 9.8. Let me clear this. Come on, baby. 9.8 times the sine of 24.0. Oops. No. Oh yeah, you're right. You're right. See, you gotta be careful with this. You're looking at a triangle upside down and stuff, so you gotta be careful. Thank you. Oops. Let me do this again. 9.8 times cosine 24.0. Okay, so I get 8.95. Let's just call it 8.9 meters per second squared. Now, let's make a note about that. The magnitude of A subscript C is just a trig problem, and try not to get tripped up like I did. That's equal to 8.9. And what I want to mention to you, that's 90-something% of, divide that by 9.8. That's 91.335% of G, of the magnitude of G. All right, so what that means is that the acceleration due to gravity is mostly centripetal at this point. Yep. Brandon, Robert, you listening? This means that the acceleration at this point is mostly changing the direction, centripetal, 91% of it. Now, down here, a little bit further down, you have about 70% is centripetal. But down here, but up here at this point, which should be a little bit closer over here. Actually, I should have done this properly. It should be sixth. This should be about right here. We should have put it right up here. Up at this part, it's mostly curving the path. And guess what? When you compute the curvature of a path, that's exactly what they do in relativity. That is the source. In relativity, it's the other way around. If the space-time is curved, if the trajectories of nearby projectiles are diverging away from each other, there's a little bit of curvature, that's the source of the gravitational interaction. We say that matter curves space-time, and it's all related to curvature. Now, the point of maximum curvature on this path is at apogee. And at apogee, the centripetal acceleration is straight down. It's all centripetal. All 9.8 meters per second squared is centripetal up here. All right. And down here, it's not zero, it's minimum. It is minimum for this trajectory. All right. So this is a good little instruction about centripetal accelerations on a non-uniform circle, but fairly easy to do. And it tells you, it even gives you a little bit of a preview of relativity and the general relativity theory of the general theory of relativity, which is the theory of space-time and the curvature of space-time. All right, now questions before I change to the new problem. Can you bring this, Tyler, can you bring the screen down so I can see everybody easily, if it's possible? Good, that's good, thanks. No questions? All right, let's go to the next task, which is the money toss problem, okay? So the money toss is for those of you guys that had a problem with, oh, wait a minute, we already did that. Doggone it. Man, the Ferrari, okay, we're not doing the Ferrari problem today. Because I don't have it with, I would do it with you, but I don't have it with me. So I have them in this big stack of papers at home. Doggone it. Yeah, we'll do it. We'll do it on Tuesday when I hand back everything. Don't worry about that. All right, now let's go to the topic of the data file in Webcourses. Can you switch me over to the laptop? Okay, we're going to put a data file, or I've already done so in Webcourses. So what I want you to do, everybody at your table, light up I told everybody to log in on the big computer into web, so everybody can see it in your group. Somebody log in to Webcourses. Everybody on the big computer. Okay, I see a bunch of you are. If you're not in there, get in there. And that way, it's just so that everybody in your group could see it. All right. And I see a couple of people with their laptops open. That's all right. Keep it open. Can you sign it from more than one place into Webcourses? Yeah. Okay. All right. So get signed in, and let's switch over to the computer now. Do you know how to get a screen grab on a Windows machine? Just from up here to down here. All right. Wow, that's cool. All right. Just text it to me. Is it somewhere? Oh, you're going to paste it?
Yeah.
Ooh, how do you do that? We need it as a GIF or a JPEG or something. Sweet. Okay. Save that somehow. Wherever you want to save it, the desktop or something. I always save everything to the desktop. I don't really use discussion. All right, now attach it to a message to me from the messaging system. Switch it back Adam, so they don't see your personal messages. All right, just attach it to yeah, so select course, favorite course. Ooh, that's Summers. You got a ton of them. Here, this one. No, that's 19. Oh, this is a fine how do you do. I'm not on any of your favorite courses.
I don't collect this.
Okay. Where are you? Okay, just type in my name, Brickner. No, not there, in the recipient box. Oh, it won't let you. All right, better find it. No. Oh, just reply to that. That'll work. Just type in anything, save it. Better type in a text. Anything. Okay. Now I'll have that. I'll be able to put it in there. All right, switch back to the. Get out of there. Get back into the courses. Boy, you're kind of not very expert on this.
It enrolls me in every single course that I'm a TA for.
Yeah, so it gets pretty tiresome, I bet. That's it, yeah. I turn back to computer. Okay, now I'm assuming everybody's in. And go ahead and I'll operate. All right, so what we're going to do is click into discussions. Go ahead and click into discussions. And then down here, centripetal acceleration data. All right, this discussion here. All right, now this is going to be gradable. All right. And I'm going to tell you what I want you to do. All right. I want everybody to download this to your whatever computer. Don't download it to the desktop machine in here. When you get home, if you're not on your laptop now, just do it when you get home. All right, download it to your home computer so you can work on it. Now, this first one here, .xlsx, that's Excel format, and then there's a CSV format, comma separated values, if you prefer that, and just mess around. I try to stay away from Excel and Microsoft products in general. So, but anyways, now here's what this is kind of an assignment for the weekend in addition to your written work. This one you'll submit here. So what I want everybody to do, one person, so you're gonna have to work it out between yourselves and your group. One person per group, type in your group name. I got two different keyboards up here. Okay, so type in your group name, the Invincible 3. Now don't type it in yet. This is when you get done. And then you're going to be able to attach your group's data file. So just check, the first person in your group, one person per group, and type in your group name and then attach the data file. All right, and it's pretty easy to do. There's a little thing up here that says files. It won't say that right now, but I'll set it up over the weekend so that you can upload your file. But now what I want to do is tell you about the file itself. So let me go. I want you to do this work outside of class. All right, I want to do a few problems for you. So go ahead and close out your spreadsheets. Finish it after, this weekend or whatnot. And don't take a huge amount of time. I want you to maybe spend an hour fooling around with it. It's a simple file, so you get it formatted up and stuff. But definitely coordinate with your teammates and see who's got the coolest graph and stuff. And then, why am I talking over you guys? Please. Try to get that done before Tuesday class meeting. I'll set the assignment due. You can't attach anything right now, so don't worry about that. I'll have to modify it after class, but I'll get that done by 8 o'clock on Tuesday morning. And then we're also going to have some written problems. And to do that, we have to work on some problems from the textbook. Yeah, Seeley. I want one representative spreadsheet from each group because I don't want to grade 100. All right. So one for me, and just that's why I want you to coordinate with your teammates and just include the best of what you got, and that'll be good. And I think if you're working in Excel or numbers, you can actually copy a sheet out of the file and paste it into somebody else's file. So anyways, just do a little bit of experimenting and stuff and see what you can see. All right. Now, I want to work on a couple problems with you. Can you switch me over to the document cam, please? Okay, so this is 21620, page 2. This is from section, what section is that? Does it say?
5.6.
Okay, this is from, 5.6, chapter 5.6, the skier problem. All right, and just so you know, Matthew, do you remember, did you have the skier problem? 2050. Did you have me for 2053? Remember the skier problem? Yeah. All right. We're going to switch it over to the computer for just a second. Okay. This is the skier problem from the, and it's highlighted in 5.6. And there's a bunch of them in 5.7 that are highlighted. I want you to study those. But let's work on this one and a couple more before the end of the hour. Okay. So, all right, switch me back to .cam. All right, so what we're going to do with this problem, can you turn it towards me so I can see the screen? Lovely, thank you. All right, so we got a skier on a, can you move the picture up a little bit? Do they give you an angle? I think it's 25 degrees. Yeah, all right. So we got a skier on a ski slope and it's tilted at 25 degrees. So I'll just kind of eyeball it in. All right. And there's a right. Triangles everywhere, my friend. 25 degrees tilt. All right. And so you got to, I'm not even going to try to draw the skier. I'm just going to represent it by a dot inside of a box. So this is a robot. And so the skier's in motion at some speed v. He's going down the ramp. So we're going to have to do components. And we're going to have to, here's another one where we have to figure out tangential and centripetal. But relative to a straight line, so it's not really curving the path. This is a ski slope. All right. So the question is, can you move it down so I can see the question? The question is, no, the question is up there, yeah. The skier's mass equals 60.0 kilograms, and task A is to figure out acceleration neglecting friction. And then if you know what, if you guys still have your web courses open, you can actually get into the textbook and look at the picture. It's in modules and then chapter 5.6. And then task B is to figure out acceleration with friction. Okay. So here's the skier, representation of the skier. And let me go down here and mark the forces on the skier. Okay, so there's a vertical force, mg. and I'll write that as a vector G. So there's the force, and then there's drawing a dashed line at about the same angle. So this dashed line is 25 degrees from horizontal. The tricky part about this is the triangles, figuring out the triangles carefully. There's a force acting on it, and then there's a force, a normal force we call it, perpendicular, we'll call it capital N. So the normal force is perpendicular or normal to the surface. And then there's going to be, and so those are the two forces acting. And so they're not going to balance. One of them's vertical, one of them's tilted off to the side by 25 degrees. So we get, we're going to have 25-degree triangles all over the place. All right. So there's going to be a net force is going to be down the ramp. That's why you ski. Okay. And the frictional force, usually we symbolize that with a small lowercase f. That's going to be friction. And it's not going to be big, but it's going to be a little bit of friction. And that's going to be up the ramp. Now we're going to up the ramp. Okay. So let me darken in some of these figures so we can get a nice image on Instagram. Nice and clear. So here's our master diagram, 25 degrees. Now, here's what we got to do. Here's what's going to happen. This normal force is from the rigidity of the snow surface. So it wouldn't really work. The only way, raise your hand if you've ever been water skiing. Wow, I would have figured a lot more people in Florida have water skied. But if you're water skiing, you'll sink if you don't have a life preserver and the boat's not going. But as soon as you get going, you don't need that much buoyancy. All right. So a surface of water will not have much rigidity force. You can float stuff on top of water. All right. Like a little bugs will float around on water, and a little piece of paper, a leaf from a tree, a dry leaf out of a tree. They'll float on water. So basically, what you're doing when you're doing water skiing is you're getting leverage from those skis, and you're getting up on the water, and you've got big skis, and so that means fewer pounds per square inch pressing down on the water. It's just enough that the water can provide a little bit of rigidity, a little bit of force against gravity. But the snow surface, quite a bit. Okay, so this is going to be quite a bit. In fact, the friction force is 50 newtons. No, 45.0 newtons. But we don't have the normal force. But we can figure out the normal force, and we can figure out the net force down the ramp by using mg. All right. So there's no net force perpendicular to the ramp. In other words, the skier doesn't spontaneously go up into the sky. All right, he just goes down the mountain. All right. And the normal force, this is really an intermolecular force with, many Avogadro's number of ice molecules, and then the Earth below that providing rigidity. Right. So the way that we figure out all this stuff, so here's the net force. In fact, let's do it from this. All right. So here's my normal. I'm going to redraw this a little bit. My normal is going to be, all right, so the way you figure out the size of the normal force and the acceleration is you go to the tip, you draw yourself a weight force vector. So this is the weight force. Okay, draw yourself a weight force vector, and then and it's going to be tilted 25 degrees relative to the slope here. All right, and then go to the tip of the weight force vector and just gently draw in a vector that forms a right triangle right here. All right, so this is the form of your right triangle. All right, let me do that in red. All right, so right about here. Now it's going to look different for everybody. And so this angle, let me call theta equal. This is theta. We'll call this angle theta, 25 degrees. So this is theta down here. Okay, and this is theta over here. All right. And now the normal force is, the size of it is right here. This is the component of the gravitational weight force that is perpendicular to the surface. Okay, so try to eyeball in a vector up here in this direction, perpendicular to your surface, and try to make it look about as long as this one over here. No, yeah, as long as this one over here. All right, so this is a little bit too long. All right, I'll make my normal force right up here. Okay, so there's my normal force. Now my net force, guess what? Is going to be right here. I'll put a little star next to it. Okay, this little sliver, this little narrow base here of the right triangle is right down there. Now the thing is, we got right triangles of the same size everywhere here. This is a positional right triangle. Here, it's the size of it's a little chunk of the ski slope, right? And this is a forces triangle, but it's proportional to this, so the same dimensions and so forth. All right. So so that little base with the star is going to be proportional to this little side of the position triangle. All right. Oops. Hold on a second. Let me adjust my microphone here. All right. So what we got to figure out here. Now I'm going to draw a bigger version of this force triangle. I'll do it down here. So all right. So here's the right angle. This is F net. This is not the normal, but it's proportional to the normal force. You know, the normal force is up here. And this one is good old weight force. All right. So, and then this is theta. And this is a right angle up here. And so it's, you know, I encourage you when you're working on your homework, draw as many triangles and make them big. And use graph paper. Because earlier you saw me make a mistake with a sine instead of a cosine. All right, so now we want to get this. We want to get this baby. All right. And then we're going to modify it. You know, when we do part B, we're going to add another force in here. All right. And that'll be all right. So here we go. So this is equal to, all right, what's 60 times 9.8? So that's 55.2. 60 times 9.8. No, 500. What is it? 588. Okay, 588. So this is 588 newtons, comma, and it should be minus 588, comma j hat. All right. Now we can't use any j hats. We got to figure out these components. All right. All right, but we know the magnitude of it. So this is the hypotenuse. So F net is going to be the sine of theta. So F net is going to be 588. Hey, wait a minute. Let me double check that. I don't believe that. Oh, wait a minute. Yeah, I guess that's right. Let's see. 60 times 9.8. Yeah, 588. Okay. So 588 newtons times the sine of 25. So what do you get? Who's got 248.5? Anybody? Okay. So let's call that 240. It's a pain in the neck. 248. I'll call it 248.5. No, 248.5. Yeah, we'll call it 248.5 newtons. And comma along the ramp. Okay, so this allows me to avoid figuring out the I hats and the J hats, but it's just the I hats and the J hats would just be sine and cosine of 25, so it's not too fancy. So there's the magnitude of our net force, and so the acceleration would be equal to this divided by the mass. So 248.5 newtons divided by 60 kilograms, 60.0 kilograms. And we're going to keep this to 3 significant figures and comma down the ramp. Okay, so we're just going to get the acceleration is from the net force, and you can make it up from the other forces, but so what is this? This is about 4 point something? 4.14. Let me verify that. Divided by 60. 4.14. Okay, so 4.14 meters per second squared, comma, down the ramp. Okay, so that's a vector statement because we've got that little. Can you bring that up and let's just double check our work. Go to the solution. Go down. So it's the solution. Oh, they've got the X components. Okay, there it is. Go ahead and show that now. Go switch to the computer. All right, so we've got. So you can see there that they did it a little bit differently. Or the calculation looks a little bit differently. And they apparently have used the X axis. They've redefined the X axis to be along the ramp. That's all right. The math is still the same. There's sine of 25 and so forth. That is weird. So they're just doing the accelerations. So they're just doing G sine 25. Yeah, that's good. That's cool. So 4.14 is good. Now let's go back up to the diagram. Now we're going to include friction. All right, now it's going to be a little different. All right, and our friction is going up the ramp. So go ahead and switch to the doc cam now, please. Thank you. All right, now with friction, F net is now going to be this force here minus a little bit of friction. So let me just pencil in a little bit of friction here. Let me make it a little bit smaller. Make it smaller than the F net part. Okay, so this is F. I'm running out of space here, so I'm going to cram that in. Okay, so this is for part 2. So So that means that the new F net is equal to 248.5 newtons minus the friction, which is 45.0. All right, along and comma along the ramp. Okay, so the net force is 203.5 newtons, comma along the ramp, and the acceleration, the new acceleration is about 5 point something. No, yeah, 3 point. Yeah, okay, it's 60. Okay, so 3 point what? 3.39. Does that look right? Yeah, okay, 3.39 meters per second squared, comma, and I'll make this a vector A along the ramp. So you can see that if you factor in a little bit of friction, not a whole lot, you get a little bit less acceleration. But if you have good skis and the snow is not too sticky and wet, you're golden. All right, let's go check this answer. All right, go ahead and switch to computer. Okay. Now, all right, so they agree with us, 3.39 meters per second squared with friction. Switch back to .cam. All right, now, does anybody have questions about, come on, there we go. Come on screen, where are you at? That's just trying. Question from the DADs. Along the ramp instead of down the ramp? I could write down the ramp, up the ramp. This should be, you could write down the ramp here. I mean, you know, I wasn't being, you know, entirely specific here, you know, given the fact that it's obvious what direction this should be, as long as you say along the ramp. But here, see here, I'm departing from that. I could put down the ramp here too, down the ramp, and here along the ramp, along the ramp and along the ramp. But yeah, see the thing is, this one is actually righteous with the new F net, because that has something positive and something negative. Now that's really the only game in town with this one. If your friction is the opposite direction to the you know the gravitational, the component of the gravitational force, the weight force, right? So as long as there's a difference in sign here, SIGN, then you're good. But yeah, you should mark down along the ramp. So we'll just go up to the original picture. Along the ramp is this way, and up the ramp is this way, and down the ramp is also down this way. So it's basically, so positive means along the ramp in that direction. So, all right, another question? Boy, look at the color of my hands. They look like they're orange. All right, like I'm radioactive. No other questions? Let's go to the next one. Can you find me that other problem? Or was that the one problem? That was the one problem that I told you. Okay. Okay, let's do another solution, another problem. And we got 20 minutes, good. All right. All right, so I'm still recording. Good. So this is 2, 13, 20, page 3. Okay, let's do the Spider-Man problem. You know that you're not going to get the Spider-Man problem, but you also know that you're going to get something similar to the Spider-Man problem. Peter Parker. All right. So let's say that we have put a dot down here to represent Gabi. Oh, wait a minute. We already used, we don't want to use G. So who's another one of his enemies? Doc Ock. Okay, so Doc Ock is right here. And Doc Ock, the mass is, let's say he's got his big Doc Ock apparatus in there. So let's say that's, for a nice round number, 190 kilograms. Okay. But because Peter Parker always figures out a way to defeat his enemies, has he ever been defeated by an enemy? But not permanently.
No, it's common. It's never permanent.
Yeah. Okay. All right. So let's say, let's say that he's got one web tilted really steep like this. All right. And let's say that his other web, this is the first web. The second web is way out here. This is the first web. Okay, so let me tilt it way out here. All right. Now, so this is web 1, and this is web 2, and Doc Ock is about to get it dropped in the water, so he cannot defeat Peter Parker. All right. Now, go ahead and draw a dotted line straight down to the position of Doc Ock. Now, this is for a mythical bridge that is completely flat. Normally, they have a graceful, slow curve, but we're going to assume that both attachments points are at the same level. Okay. Now, so there's the trap that Doc Ock is in. Right. I'm going to draw some arrows of generic size to represent the pull force or tension T1 from, no, that should be that's web 2. This is web 2. So this should be T2. Okay, so there's the tension or the pull force from the second web. And then I'm going to draw the same size arrow here simply because we don't know the sizes. So we'll just kind of draw them some generic length. And so we want to figure out T1 and T2. All right. Now, what you do is you add up all the forces. Now, Doc Ock is standing there or sitting there, cursing Peter Parker. All right. And so he's stuck. So all the forces balance. He's not accelerating. He's stuck. All right. So are those the only two forces that are acting on Doc Ock? Got gravity. All right. So let's make a big vector down, and I'll make it a blue vector. Now we don't know the relative sizes of these forces yet, but we do know that it's equal to mg. All right. And we know the mass of Doc Ock. So let's figure this one out first. Well, what's 190 times 9.8 meters per second squared? Negative. So this is j hat. All right, and we're going to use I hats and j hats here. All right. So what does that work out to be? 1862. Anybody verify? Yeah, okay. Negative 1862. I'll write that down here. Negative 1862. Is that right? Yeah, okay. Newtons, comma, j hat. All right, now. So this is what you would call a free body diagram, except we don't know the relative sizes here. We're going to compute the numbers and then maybe resketch, but at the minimum, let the numbers do the talking. All right. By the way, which do you think is going to be the biggest tension, T1 or T2? You know, I should have done an iClicker question for this. Nice, but I closed down. Doggone it, I closed down the iClicker. All right, so let's get this sorted out. A lot of people say T1, some people say T2. Let's let the numbers do the talking. Now, what we know is that we have equilibrium. Because Doc Ock is at rest. So all the forces balance. Now what that means for us is that the X forces balance and the Y forces balance. All right? So let's try to figure this out. The sum, I better write this in ink so it's really clear. Okay, the sum of all the forces in the X direction is equal to 0, 0.0 newtons. Okay? And then the sum, this, you guys have had calculus, so you know this is a summation sign, of all the Y forces is equal to 0.0 newtons. All right? So that means that T2Y plus T1Y minus mg, or plus mg, I should say, those are going to be equal to 0. And then T1x and T2x are going to be equal to the same size. So this means T1x plus T2x equals 0. And this one means that T1y plus T2y plus W is equal to 0 as well. All right, now that's the key. So if you have equilibrium, this is the law, and it's going to actually allow us to figure everything out. All right, so let's start with the X components. T1X is, oh, we gotta give some angles up here. So let's get some angles up here. So let's call this one 25 degrees again. All right, and this one's steeper, so let's call this one up here 55 degrees. All right, and we're just gonna let the numbers do that. I don't know if this is a good 25 or a good 55, but they're fairly close enough for government work, so we'll let the numbers do the talking. All right. Now, T1 is going to be on a triangle like this. All right, so here's T1, the magnitude, and then here's T1x, and here's T1y. And then over here, the T2 triangle is a little bit steeper. So here's T2, and here's T1, or T2y, and here's T2x up there, okay? And the direction of the T's are up here in this direction, okay? So T2x is going to be positive, and T1x is going to be negatory, right? So remember that. We also know the size of these angles, 25 over here and 55 over here, all right? And that's going to let us do a little bit of trig. And we also know, we actually know the magnitude of this baby over here. Okay, so let's put the x equation together first. All right, so T1x is T1 times the sine times the cosine of 25. And it's going to be, let's put a minus sign here. You know, you could either put a minus sign here, or you could put, so what would that be? The sine of 155, or the cosine of 155, which would be the negative of the cosine of 25. So that's E plus T2. So T2x, oh, man, I'm blooping this up here. This is T1x, T2x is up here. So you know what? This is messed up. I have this triangle up here messed up. All right, this is 55 up here. There we go. That looks better. All right. Nobody caught me on that. Do not let me catch you napping. All right. So T2x is T2 times the cosine of 55 equals 0. So that means that T1 time negative, so T1 times cosine of 25 equals T2 times the cosine of 55. All right, so that's all right. So we could maybe use the ratio of T1 over T2 to substitute in or something like that. We got two unknowns, and T1 and T2. Now the second equation for the y components, and this one's a little bit longer, T1y. So T1y is positive. Both of these are positive. So this is T1 times the sine of 25 plus T2 times the sine of 55. Okay, those are both positive. And then minus or plus a negative 1862 newtons. And that's equal to 0. All right. So here are my two equations. All right. So these two equations right here, two equations, two unknowns. So we can figure out for T2 and T1. So we just got to do some elimination here. So it's kind of a pain in the buttocks. You know, it might be nice. Let's try to. Anybody have an idea of what to do? I do. There's a billion different ways to solve for T1 and T2. And once you get T1 and T2, you've got everything you need because you already know their angle. Substitute what for what? So you want to take this equation and say T1 equals T2 over cosine 55, or T1 equals T2 cosine 55 divided by cosine 25? You think? All right, let's do it. All right. So substitution, and that's coming from the, what is your guys' group name? The what? The Best Bunch? The Besties. The Best Bunch. Known as the Besties. All right. So T1 equals T2 times cosine. So we might get some tangent of 55s in here when we substitute it in. Divided by cosine of 25. All right, now let's put that in over here. All right, so T1 is now this junk. So T2 times cosine 55 times sine of 25 over cosine of 20. Yeah, so there's a tangent of 25 plus T2 times sine of 55 degrees minus 1862 newtons equals 0. Okay, so we've just about got it. Go ahead and grind it out. You see what to do? All right. So we've reduced two unknowns to one unknown, so we just got to do a little bit of nasty. Oh, wait a minute. No. Yeah, don't. Whoa, you know what I almost said? Let's cancel here, but you can't. They're two different cosines. So you can't do that. You just got to grind it out. Okay, so we're now at the grind out stage. See if we can do this real fast and then dismiss. So cosine 55 times sine 25. You know, this is pretty nice with a calculator. Divided by cosine 25 equals 0.26656, no, 0.266, yeah, 2656 times T2 plus sine of 55, 0.1915 T2 equals 1862 newtons. So that's parking the negative 1862 on the other side. Okay, so this plus 0.2656. Oops, I messed that up. 0.2656 plus 0.81915. So I've got 1.08475 approximately times T2 equals 1862 newtons. So T2 is going to be ginormous. It's almost 1862 newtons. So that means that T2 is doing most of the upward pull and only a little bit from web 1. All right, so okay, so T2, anybody verify me? 1716.5 newtons. Anybody verify me or close to that? Yeah. All right. So now we just have to put that back into this formula up here, and then we'll have T1 and T2. All right. Now I'll leave that as a exercise for you to do at home before you do the homework. All right. So my wonderful students, you now know the bare bones You're not going to get a Spider-Man problem, but the Spider-Man problem that we have just done will help you with homework 4. All right, now I'm going to, let me say one more thing about homework 4 before we dismiss. And let me just advance the slides. Can you switch me over to laptop, please? Okay. I want you to read ahead, complete everything that you want to do in Chapter 5. I've highlighted a bunch of problems. And start to skim Chapter 6. The PDF will be about supper time tonight in Webcourses, and then due on Tuesday. But one more thing. Even though you've done the Spider-Man problem with me today, and improvised, I didn't know what, I just made it up as we went. But it seems like we all got everything correlated. Even though we've done this new version of the Spider-Man problem, you're going to find it a challenge you're still going to find it a challenge to do the homework tonight or over the weekend, simply because, it's probably your first time going through this kind of stuff. But if you follow the techniques or your own techniques and then compare them to mine, and because as I've said many times, there's more than one way to skin a cat in physics. All right. So you may see it a little bit differently than me. Study the book. They'll have a different outlook, and see if you can get some wisdom out of those two sources in your own way, and then do your best. Okay, you're dismissed. I'll see you on Tuesday. Christina. Yeah, patience, Christina. Didn't I hit back something to you already? Your quiz? Oh no, yours is the one that I didn't finish grading. Yeah, I got to do a bunch, but you're gonna be enthused, be encouraged. Yeah.
This is on Christina's desk, but she isn't here.
Christina.
No, Christina.
Oh, okay. All right. Never mind. It's different Christina. Salyers. Was she here already? Why did you hand out her paper?
I thought you was nice.
Okay. All right. Thanks. Natalie. Go ahead.
Can you tell if the T is going to be negative or not?
Yeah. If it's this is T1x. Okay. This whole thing here. All of this is T1x. And it's a leftward pointing vector. So this thing's going to be a negative number. All right. So that's because I always treat T1s as being positives. The hypotenuse as being positive. All right. But then you want to make sure that your components are either are leftward negative or downward negative, rightward positive or upward positive. All right. It's tricky to keep in mind, but that's how I do it. The alternate, you can also write
So when we T2, we can just plug in for T1.
T1x
Pin?
equals T1 times the cosine of the supplement of that, which is 155 degrees. And then this is going to be a negative number anyways. So then you don't have to put a minus sign up front. But I always think about the angles inside the triangle. Right? So I always think about this. Instead of this one would be like, here's T1.
So depending on how you define your
And here's the x-axis. And this angle, that's 155 degrees. Okay, so some people think in those terms. And I'm always focused on the inside of the triangle. But so this one's good and this one's also good. So, alrighty?
Also, it says the calculation of my grade in Webcourses is not
Yeah,
available.
that's right. I shut those down till the end of the semester. I'll open them back up again. Okay, and because then it'll make a lot more sense. Until the end of the semester, like sometime in April, it's all the they only know how to calculate percentages, and they don't know my percentages. You can't, it's not nothing. There's no spreadsheets or anything inside Canvas, so you can't really do any tricky calculations of grades the way that we do in this class. So that's why I shut it down until the end of the semester. But eventually you'll see it. Yeah. Question?
Okay, turn this off. So.
Oh yeah.